Hey guys, this is Professor Janacek, and I want to introduce you to functions in several variables. To begin with, we know about functions in a single variable. That would be like y is equal to f of x. Again, this is a single variable. And what we mean by variables, we mean we have a single independent variable. We do have a dependent variable, that's y, but our independent variable is x in that first situation. Looking at this next one, z is equal to f of xy. In this case, this would be a function in two variables. And the idea here is that we have two independent variables, x and y. Z is called the dependent variable in this situation. And then finally, w equal to f of xyz would be a function in three variables. And so here we have x, y, and z are the independent variables, and w is our dependent variable. Of course, we could continue on and have as many variables as you'd like. Let's take a look at some examples working with these. First, let's see if we could determine the domain for f of xy is equal to 1 over the square root of x squared plus y squared minus 25. You'll notice that my function here, I have both x's and y's in the function description. So let's see, what do we need to know about this one? Well, just like all of our other functions, we cannot divide by 0, so I know that denominator has to be cannot be equal to 0. Furthermore, I know that whatever's inside a radical cannot be negative. So if I put those two ideas together, I know that x squared plus y squared minus 25 will have to be greater than 0. Because one, it cannot be negative because it's inside the radical, and it's in the denominator, so it can't actually be equal to 0. Well, that tells us that x squared plus y squared has to be greater than 25 if we move our 25 around. And that's one way of simply writing this. We can write that the domain is the set of all not just x's, but the set of all x's and y's, such that x squared plus y squared is greater than 25. So you can use set builder notation in this case. We could also describe it in words. You might recognize what this looks like. It's very similar to x squared plus y squared is equal to 25. That should be familiar to you. In fact, that's the equation of a circle, so we could say that this is the set of points. Now this is actually greater than 25, so that would be outside the circle. And from that equation, you should be able to pick up that it has a center at the origin with a radius of 5. And there you go. That is our domain. Again, set builder notation might be something you're familiar with. All right, on to example 2. Let's determine the domain of g of x, y, and z is equal to 2xyz minus 3xz plus 4yz. So here we have a function in three variables, three independent variables. You'll notice this does kind of have the look of a polynomial. It is rather polynomial-esque. And if you remember back in single variable functions, polynomials were basically defined everywhere from negative infinity to positive infinity. And that's the case here. And so we can basically say it's the domain is all real numbers, but what is our all real numbers? Well, in this case, because we have three variables, we are actually looking at R3. Oops. So our domain for example 2 is 3 space, or R3. On to example 3, let's determine the domain and range of h of x, y is equal to 2x squared plus 3y squared. So here we have a function in two variables. This time we want both the domain and the range. Well, looking at it, we could probably guess that the domain is going to be R2 because it is, again, a polynomial. But hopefully you'll recognize what this looks like. Let me go ahead and just do a few things. This is z is equal to 2x squared plus 3y squared. And if you remember this, I could write this as x squared over 1/2 plus y squared over 1/3, which is the same as z is equal to x squared over the square root of 1/2 squared plus y squared over the square root of 1/3 squared. Now, why did I go through all that trouble? Because at this point, hopefully it looks familiar. This should look like z is equal to x squared over a squared plus y squared over b squared. And hopefully now you recognize this. It is an elliptic paraboloid. So knowing that, we can actually kind of sketch a real quick graph. It is because x and y are not being shifted left, right, up, down, front and back, however you want to think of it. There's no shifting going on. We know that it's centered at the origin, but it looks kind of like, I guess, like a cup, some sort of vessel. And it's sitting here on the xy axis, and the z-axis comes right up through the center of it. So now looking at it in this way, again, my domain is the xy, is what's going on in the xy plane. So as far as the xy plane is concerned, you can see things will continue on indefinitely. And as we saw before, it is polynomial in a sense, so its domain, we're looking at R2 space, everything in the xy plane. However, in the z direction, notice that would be my range, because here we have my dependent variable. Again, it's z equal to this stuff in terms of x, so z depends on x and y. Therefore, my range are the z values. What are my z values? Well, in this case, you can see that I'm only going in the positive direction for z. I don't need to go down. There's nothing going down this direction. So as far as the range, we're going just from 0 on the z-axis, right down there, all the way up to positive infinity. So there we go. That is the domain and range for this one. I also want to just briefly mention another idea that we can kind of get from this that's called level curves. Now, level curves, also called contour curves, you can kind of see what those look like. Here we have a curve. There's a curve. Looks like that nice smooth hill. And what we're going to do is we're going to take a plane. So here I've got a plane, and I'm going to slice through that curve, and I get I'm going to take the plane, slice through that surface, and that gives me this curve. You can see slicing it with a different plane. If I use this blue plane, I get a different curve. So slicing a surface with a plane. Remember, surfaces can move, but planes are flat. So I'm going to slice it with a plane, and that gives me what's called a level curve. And you'll notice, so this level curve down here corresponds to this circle in the xy plane. This level curve up here corresponds to this ellipse in the xy plane. Not circle, sorry, they're ellipses. And that's why it's you would see that this would be an elliptic paraboloid as well. So you can see kind of the connection. I'm taking those planes and cutting that surface. Now the way we describe these is we would say that our f of x, y is equal to k for k a constant. Now how to find these? Well, we can pick some constants. Let k equal to 0 and put it into your equation, and let k equal to 1 or -1, and that will allow you to kind of determine what those curves look like. And then of course we would simply graph it in 2 dimensions. Notice again my surface is in 3 dimensions, x, y, z, but my level curves or contour curves, those are only in x, y. So you can simply replace the z value with a constant and then graph that curve. You can see that we would also have this idea of a level surface. It's just an extension of the level curve idea. So not too bad, I hope. Enjoy!